surrounded by people who have been at Davis at one point or another, and it's really great to see old friends here. As long as you made a plug for my summer program, let me add a plug for my summer program. I do direct the California State Summer School for Math and Sciences at UC Davis. I've been doing it for 13 years now, and it's a summer program for talented high school students. It covers all areas of math and science, and this summer we're having 212 students who are just about to be admitted, and they live on campus for a month, and they study all kinds of things, and it's really a terrific experience, and I even have some people who can vouch for it, I think, in the faculty room there, because one of their daughters was at the summer program, and she's off contemplating which extremely prestigious college she's going to attend, so that's exciting for us. So let me start my talk proper. I'm going to talk a little bit about the topology of the universe, which is a mysterious thing, it turns out. So, over the course of the last 5,000 years or so, people have thought about this in one way or another. It sort of depends on where you're from, how you thought about it. So there's the point of view of the Central Valley of California, which is where I'm from. And as you can see from this picture, from the point of view of the Central Valley, well, so now what I'm really thinking about is what does the Earth look like? So if we go back 5,000 years, people weren't so sure what the Earth looked like. And I know that the Central Valley didn't have row crops 5,000 years ago, but it was still flat. So, 5,000 years ago, if you were in the Central Valley, you probably thought it was pretty flat. And so people did wonder about this. They got all kinds of different ideas. They wondered what would happen if you were bold enough to sail beyond the Pillars of Hercules. And it used to just say on maps, beyond here there are monsters. That was about it. That was all anybody knew. There was just wasteland out there as far as people were aware. And there were other ideas about what the surface of the Earth, what the shape of the Earth would be. So this was one worry about what might happen if you sailed beyond the Pillars of Hercules. If you went a little too far, that would be sad. So until Magellan didn't make it back, actually, sadly, but his ship made it back. His ship sailed around the world and actually went around the world. Got back, and everybody said, okay, well, that settles it. The world is not flat. You won't come to the edge of the world and fall off. You may die halfway there, but you're not going to just fall into a pit. And so now, today, we're pretty sure that the world isn't flat. But people did think the Earth was flat, and it turns out that some people still do. And so this was a fun thing when I was getting ready for this talk. I discovered the International Flat Earth Society. And here are some headlines. These were, I have to say, I've stolen fairly freely from the web. So, headlines from the Flat Earth Society: the whole world is deceived except the very elect. Galileo was a liar, and my personal favorite is the world is flat, and that's that. So, despite all evidence to the contrary, there's still at least one small group of people that believes this, and you have to be grateful because that means that there's still one small group of people on the Earth that it's reasonably safe to make fun of. So that's, I hope I didn't offend anybody. But I'm pretty sure that the world isn't flat. Okay, but now what I'd like you to do is imagine that there's an apocalypse. So probably the members of the International Flat Earth Society spend a substantial amount of their time imagining there's going to be an apocalypse soon. But we can imagine an apocalypse without any help from them. So there's some kind of gigantic electromagnetic pulse. I have a story about that. There's no transportation. There's no Google. I don't have to have my let me tell you about the gigantic electromagnetic pulse. So this is something. This sounds like the like delirium of crazy conspiracy person, right? A gigantic electromagnetic pulse that's going to take out all of our entire communication system. The U.S. Army, it turns out, prepares for this event. I discovered this when my nephew, who was in the Army, was studying for his captain's exam. And in aid of his studying, he pulled out 3 very complicated slide rules. So how many people have ever seen a slide rule? Yeah, well, the average age of the people that seen slide rules is, we won't go into that. But remarkably enough, one of the requirements for this exam was that he be able to calculate trajectories of things. We don't want to discuss what things exactly, regardless of whether there was a gigantic electromagnetic pulse that took out all of the computational equipment they had. And so he had to be able to do it with slide rules. So I was impressed by that. In some way, I was impressed by that. It was a lot. Anyway, so you imagine that there's something like that. There's no communication. The only 2 people left are you and one member of the International Flat Earth Society. And your job is to convince this person that you're right and that he's wrong and that, in fact, the Earth is not flat. And this is a problem, it turns out. What can you say to convince somebody that the Earth isn't flat? Well, there are things. There always were things that made people think the Earth wasn't flat. It didn't take until Magellan went around the Earth for people to decide the Earth wasn't flat. There are a bunch of things, and those things still exist, regardless of whether there's efficient communication or not. The shadow of the Earth on the Moon, for example, is not, well, that's a little iffy, right? Because you remember that disk picture? You could get a kind of curved shadow there. It's a little hard to explain, but still. Ships disappear over the horizon, so that assumes you have some kind of a ship and you can see far enough, but in fact, if you watch a ship go far enough, it doesn't just drop out of sight instantaneously, it actually sort of sinks rather than going off a cliff. Shadows of sticks in different locations at the same time, so that's a little bit trickier, and also you have to be able to get from one spot to the other, or you have to have 2 people who are agreed about something. But if you have a sun here, and you have a stick here, and you have a stick here, reasonably far away from each other, the lengths of their shadows are going to be different depending on where they are relative to the sun. But you have to be pretty far away, and the sticks have to be pretty big to be able to measure that difference. Nevertheless, that difference exists. So that's something that you could look at also. Now, there may still be some shreds of direct evidence, like photographs from satellites or something, but since the members of the International Flat Earth Society have explanations for these photographs, at the moment it doesn't seem likely that that's going to help very much. So this may make you feel better, but I don't think it's going to do very much here. So really you're going to have to rely on indirect evidence if you're going to try to talk somebody into the Earth not being flat. And one of the things I want to emphasize is that thinking that the Earth was flat was not stupid. In fact, it was relatively clever. Not so clever if you're from the Central Valley, because the thing looks flat. But if you're from a kind of a hilly region and you're not sure what's going on around you, thinking that the thing goes on forever and is basically flat is pretty good extrapolation from your local information, right? So it wasn't that it was stupid, it's just that people were dealing with very limited information. Okay, well, so anyway, good luck with the Flat Earth Society. So now let's picture the year 3000, And the Kieval lectures will still be going on. Hopefully they'll be, I don't know, more efficient or something. I don't know. But and the lecture begins once upon a time. And you know, it's the year 3000, and so their timeline is a little bit, who knows, what happened 1,000 years ago exactly? Nobody's really sure. So on Earth around 2000 AD, and other places in the universe, a long, long time ago, the lecturer starts. People thought that the universe was flat. Now, you and I know that this isn't from 2000 AD, but it's pretty close, right? The universe was flat and had an edge. So I'm very fond of this picture, so I admit that this universe doesn't look so flat. On the other hand, it clearly has an edge because this poor man has stuck his head and his hand out through it and is reaching for the heavens, I gather, because I think those are wheels within wheels up there, which is quite nice. But in any case, he's gone to the edge of the universe, and he's stuck his head through, and he's looking for what's past that. It's an idea of what the shape of the universe is. And we have an idea for what the shape of the universe is, and we don't even think about it very much because we're living in it. So here we are, living in the universe, right? This is the universe. Now, we're not seeing a really big region of the universe, but as far as we can tell, it looks kind of ordinary, you know, like you took your table and you added one dimension and that's it, you got the universe. So what I want to try to describe to you is some other possibilities. So for the rest of the talk, I'm going to try to describe some toy models of the universe, 1- and 2-dimensional toy models of the universe. Try to think a little bit about what it means to say the universe is flat. Does that even mean anything? Think a little bit about what it would mean for the universe to have an edge, or for any space to have an edge. Construct a couple three-dimensional possibilities for the universe. And 2 of those possibilities are flat in some pretty precise sense of the word flat. They don't have an edge. They have a finite volume. And they have some other strange features, which I'll try to describe. And then for extra credit, if we get to it, we can talk about what 11-dimensional space is, because that's what the physicists are all excited about. But that's just a brouhaha, so we don't have to worry about 11 dimensions, really. Okay, so that's the plan for the rest of the talk. So first of all, dimension. What is dimension? Dimension is one of those ideas that mathematicians just think is completely straightforward and everyone else thinks is really mysterious, or slightly mysterious at least. And mathematicians are right, it's completely straightforward. Dimension is just a description of how many pieces of information you need to locate a point in a particular space. That's all. So we say that something like this is one-dimensional. The points on this curve is one-dimensional. Why? Because if I pick a specific point, I'll call the origin on here, and then I tell you a distance, like 3 inches, I might have to say to the right, but let's say 3 inches to the right, everybody will arrive at the same point on this space. One piece of information, everybody lands at the same spot, right? Same thing on this circle, not the inside, just this edge here. If I say, okay, everybody imagine an x-axis out here, and now I'll tell you a degree measure, like pi halves. Everybody in the room is going to land at the same point on that circle. One piece of information, you land at the same point on that circle, right? Okay, so those are one-dimensional spaces. They're not very exciting. We'll take them. 2 dimensions. Well, we live on a 2-dimensional globe, right? We live on a 2-dimensional object, which is the surface of the Earth. So 2 dimensions I'm representing here by a sphere, which is hollow. And, well, we navigate around the surface of the Earth with 2 pieces of information all the time, right? Latitude and longitude, right? That's just 2 pieces of information, locates, without a doubt, any point on Earth, right? That's what GPS is good for. Okay, now this is I've done a couple things here. That's a solid ball in the bottom right-hand corner. So it's 3-dimensional because if I want to locate a point in that object, so I need 3 pieces of information. So what kind of information do I need? Well, an efficient way to do it would be to locate a point on the surface. Like I could use latitude and longitude to locate a point on the surface and then tell you, and now meet me 3 miles deep or something. It would be silly, but we could meet 3 miles deep at, underneath Manhattan or something. Well, maybe underneath the corner of 55th and 3rd Avenue or something. It might be we wouldn't want to mess it up, right? If we're going to dig 3 miles down, we want to be in the right spot. So it takes 3 pieces of information to locate a point in this ball. Okay? Now the ball also has an edge. That is, if you're a mole and you're crawling around inside this ball, everything looks pretty much the same unless you get to the edge, right? Unless you get to the surface of the Earth. So that's a little bit different. The fact that this thing has an edge from the point of view of something that's living inside here, and this doesn't, right? You don't get to any edge here. There's no big sign that says you are passing the equator now as you go across the equator, right? That's just an artifact of our maps. So this doesn't have an edge, and this doesn't have an edge. This has an edge. This doesn't have an edge, but this one also keeps going, apparently, forever. So that's a little bit different, too. So these are different mathematical spaces that if you were a 1-dimensional or a 2-dimensional or a 3-dimensional creature, they would look different from each other. Okay, so that's the idea of dimension. And while we're here, let me just draw you a few more 2-dimensional spaces. So these are hollow. These are surfaces. So the one on the left, the 2-dimensional sphere, we've seen already. The next one is the 2-dimensional torus. And you should think of that as just like the surface of a bagel, surface of a donut. But just the surface, not the inside part. You don't get to eat just the surface part. And then the third one is what happens if the baker has a really bad day and starts putting extra holes in things. And so that's sometimes called a 2-hole torus. Again, it's just the surface that's involved here. And once you've gotten that idea, of course, you can keep going forever, right? Just punching more holes in the thing. And those are, so that's almost a classification of surfaces. There's some other interesting surfaces which probably you've seen. Non-orientable surfaces. So this is supposed to be a picture of a Mobius band. Does it look like a picture of a Mobius band? Yes, okay. And so a Mobius band is 2-dimensional, right? It's if you wanted to locate something in the Mobius band, you could tell me where it was around this circle and then where it was in the crosswise direction, right? But if you lived in the Mobius band, it has a very disconcerting property. Namely, if you lived in the Mobius band and happened to be completely a right hand, it's limited existence, but nevertheless, if you lived here and you were just one hand, and you took a long walk, you walked all the way around the Mobius band. So here you are, your right hand, you walk all the way around the Mobius band, and of course I can't actually do this. What's happened when you get back to where you started is that you have turned into a left hand, right? That's why the Mobius band is said to be non-orientable, because you can't keep the orientation of your hand correct if you live there. And it's important that you live in the Mobius band rather than on the Mobius band. So this is really just gratuitous, because this is one of my favorite pictures. This is a Escher picture of ants crawling on a Mobius band. And of course, nothing happens to the ants because they are not living in the Mobius band. They're three-dimensional creatures just crawling around on the top of it. So, as I said, that's just a gratuitous nice picture. Okay. So those are some spaces that we were interested in. And now I'm going to come to something that's going to cause me to pause for a minute, because I want to go back to the torus. So this is once again a picture of a torus, the surface of a donut, the surface of a bagel, just a surface, two-dimensional object. And what I claim is that the torus is intrinsically a flat space. So I want to explain what I mean by that a little bit. It turns out that for surfaces, the idea of curvature is really simple. And I was going to bring like a mannequin with me, and then I realized, here I am. So I'm going to illustrate curvature on me. So when you're on a surface, it's an amazing fact that the surface will curve in two perpendicular directions maximally. That is, so here, like at the shoulder, I see a line of curvature here, and it's curving down pretty steeply, and perpendicular to that line, I'll see another line of curvature here, right? And you can see that both of those are curving in the same direction, right? And in fact, if I pick any two perpendicular directions right here on the peak of my shoulder, both those lines of curvature are going to go the same way. But the perpendicular ones are the ones that curve the most, those two that I picked out in the first place. And there's always a perpendicular pair that curve the most in some sense of that. And if the directions of those two lines, the curve of those two lines is the same, we'll say that this point is positively curved on the shoulder. So right here, that peak of my shoulder is positively curved, okay? Okay, now unfortunately I didn't wear a long sleeve shirt, so that's, okay, so you may have to imagine things here, because I'm not going for the underarm, I'm just not. So, let's instead look right here at the crook of my elbow, and imagine that I'm gonna hold my elbow like this, right? And so the two perpendicular directions to pay attention to in this case are this one, right, that goes around my arm like this, and this one. And if you think about those two lines of curvature, they're going in opposite directions, right? That point right here is negatively curved. You can think of one of the directions is giving me a +1, one of the directions is giving me a -1. When I take the product, I get -1. It's negatively curved, okay? So for anybody that's ever tried to sew a shirt, has anybody ever tried to sew a shirt? This may not be the right audience. Okay. One of the worst problems when you're trying to sew a shirt is trying to set a sleeve. Right? Yeah, right? Trying to set a sleeve is a nightmare. And it's completely clear why from the point of view of mathematics, because this point on your body is positively curved on everybody, really, I promise. It's positively curved on everybody. And this point is extremely negatively curved. And it causes all kinds of havoc with the geometry of the shirt that you're dealing with. And so you get this funny kind of curvy line that you're supposed to match up to the edge, and it doesn't work very well, honestly. So this is the geometry of shirts, but it's also just the geometry of a surface. So there's positive curvature, there's negative curvature, there's a lot of flat stuff. So if I look at a point right here on my arm, it curves positively this direction, but it's dead flat here. This is actually flat. It's like I took the product of +1 and 0. I get 0. And you can see that because you can take a flat piece of paper, a flat piece of cloth, and drape it over your arm here with no problem at all. Right? It's flat. Okay, so the claim is that the surface of a torus is actually really secretly flat. And the reason is that if I cut a torus open, which I'm about to try to do, how this line would work, but this is just a bicycle tire, which is a perfectly good torus. And if I cut it, so I cut it like that, and then it's going to take a while, but if I cut it like this, I think I'll make it a shorter torus here. If I cut it like this and lay this piece down, I can actually flatten it out completely in the plane. So it's somehow intrinsically flat. I could put a geometry, a way of measuring distances on this surface so that it'd be indistinguishable from regular Euclidean two-dimensional space. Okay, that was my diatribe on the torus. Okay, what about time? We were talking about dimension, we're talking about different spaces. Why does everybody, you get that weird, NPR voice, time is the fourth dimension. And time is it's very reasonable to think of time as an additional dimension, but it's not very complicated to think of time as an additional dimension. So this is supposed to be a picture of a one-dimensional universe. Remember, we can think of universes as being any dimension we want. So let's just think of it as being that circle, one of the circle that I started with. It's a circle, and so physicists are very focused on this. It seems to be expanding. It's getting bigger. Well, there are lots of things that are circles that are getting bigger as they go out, like an ice cream cone, for example, right? It's just a circle, and it's getting bigger as it goes up, right? So I've drawn a picture of one. Here's a circle. It's getting bigger as time passes, so time is passing in this direction. That's the Big Bang, right? So that's kind of a worrying thing from a mathematical point of view, but it's okay. It's a singular point of this. This is an intrinsically two-dimensional object. There's one dimension for the universe, and then there's one dimension for time. And you really have to think of it as just like a two-dimensional space. And so one of the things I've drawn here is it's good to think about what happens to light, for example, or sound even, in the universe. Well, comes of being a mathematician. The two people are creatively named A and B. A turns on a flashlight towards B, right? And B thinks that he's getting that flash of light instantly, but of course he's not. Light takes time to travel. So the path of light in this space is actually along here, right? It actually travels both through time, this way, and through space. So it does get to B, but it gets to B a while later, right? After it has to travel there. And so B doesn't really see, B actually registers the light that's coming from A well after A may have turned the light on. Okay, so that's a good thing to keep in mind. Okay, that's a one-dimensional universe. That's not too exciting, unless you're like an ant. So I think I've said this, adding time to the picture just adds a dimension. So this is sometimes called a 1 + 1 dimensional universe. And all of these things are possible because instead of an ice cream cone, it could expand out for a while, then contract in, and then expand out and contract in. There's nothing really intrinsically preventing any of that from happening. And unfortunately, there's also nothing preventing it from expanding out for a while, contracting in for a while, and then just disappearing in sort of the inverse Big Bang event. Okay. Well, as I said, one dimensions aren't too exciting. So what about two dimensions? What if we have a two-dimensional universe? So remember that poor left hand stuck in the Mobius strip. Well, maybe the universe is two-dimensional. It again starts with a Big Bang, and as time passes, it's a two-dimensional sphere, and that sphere is just expanding out as time passes. Or maybe then it contracts for a while, expands out. Who knows what happens? That's a possibility. That's not a realistic possibility because we seem to have more than two dimensions move in. But as a thought experiment, it's a good possibility. And here's another thought experiment. What if we imagine a two-dimensional universe starts at a Big Bang, and then there's the surface of a donut, surface of a torus, and it expands out as time passes. There's actually nothing intrinsically wrong with that model, except that the dimension is wrong for us in reality. Some people find it very disturbing, the idea that you could start with the Big Bang at a point, and it is a point, as you know, you can't really see it, but it's some kind of singular point at an instant, and instantaneously thereafter, the universe is somehow a torus, a donut, rather than like a sphere, which is the kind of instinctive feeling for what it should look like. It's sort of an instinctive gut reaction that we have, but there's no basis for it in mathematics. There's no problem with this occurring mathematically. Okay, so we really need a three-dimensional universe because we appear to live in 3 dimensions. So let me just take a second to talk about 11 dimensions. Why do physicists always insist on 11? They insist on 11 because they're trying to make rather elaborate equations work out properly. And the reason that we can't detect the extra ones, so one of those is going to be time, let's say. 3 of them we can see. So what am I down to? 7? So I need 7 more somewhere. So what can I do? Well, I could tuck them away somewhere. In fact, I could make them so tiny that we can't ever possibly detect them. And essentially that's the state of the 11 dimensions right now, is the idea is that they're so small that we're not going to be able to detect them. So that's a little tricky as an idea, because it means that secretly we're 10-dimensional creatures. Because if imagine that this is actually a piece of paper, so I said this was flat, this is a piece of paper, but it's not really a piece of paper, right? It's got some thickness. It's not really 2-dimensional, this object. It's got some, tiny, but it's got some thickness. Now, if you're really a 2-dimensional creature, living, say, on the upper surface of this object, well, if you're really 2-dimensional, you can actually disappear. You could just sort of step slightly to the side, and you'll be on the bottom layer of this object, and you'll disappear, and it doesn't make any difference how thick this is, right? If you're literally a 2-dimensional creature living in a literally 3-dimensional object, you can disappear. And we don't seem to do that. We don't tend to blink out that way. So that's why we have to be, if we were really 3-dimensional creatures living in a 10-dimensional space, we would sort of be able to sort of step to the right and just disappear. And that doesn't seem to happen. So they can worry about the 10 dimensions, and we'll worry about the 3 dimensions for now. Okay, so 3 dimensions. So what have we got? Well, we live on the surface of the Earth. So what about a 3-dimensional version of the surface of the Earth? So what does that mean? Well, in math, we do a lot of things by analogy. So we start, for example, with a circle. That's not just to look like a circle, it really is a circle. And so I've given a description of the circle, which is I just take two arcs, two pieces of string like that, and I describe the circle by saying, well, take those 2 guys and glue them together along their boundaries like that. And that gives me a nice 1-dimensional space, right? How about the surface of the Earth? Just the surface, not the inside of this ball. The 2-dimensional sphere. I can describe it in a very similar way. I can take an upper hemisphere, which is really just a disk. It's just a flat 2-dimensional disk, right? I can take an upper hemisphere, and a lower hemisphere, and I can glue them together. In fact, that's how you make a nice globe, right? You just glue them together, make a nice globe. And notice that this has a big advantage because these pieces, if I curve them, I can't get those pieces to lie in a plane. But if I don't curve them, if I just draw them flat, I could just draw them like that, in the plane of the blackboard, and say, okay, the space that I have in mind is what you get by taking one of those guys and one of those guys and gluing them together along the edge. And it's not perfect. There's distortion here, but if you had to travel to Australia for some reason or something, and this map was available, you could sort of set off here from Humboldt somewhere, and find your way down to Australia using this map, this atlas of the Earth, right? Does that make sense? Okay. So to go up one dimension, we just take every object that we have there and take it up one dimension. So instead of two two-dimensional disks, the upper hemisphere and the lower hemisphere of the Earth, we take two three-dimensional balls and say, okay, the space I have in mind, the universe I have in mind, is what you get by taking those two three-dimensional balls and gluing them together along their boundary. And, well, I can't do it in front of you because it's a three-dimensional space. It's a little bit hard to visualize, and besides, it can't be done. But as an atlas of an object, as information about this weird object, this weird three-dimensional manifold that I'm talking about, it's perfect. You could travel around in there. You could find your way to the other side. And, since I was promised rockets, there, let's think about this for a second. If I have these are solid balls. So if this is the universe, then if I start from here and launch a rocket with directions, the directions are just go straight. That's it. And it's a good rocket. It goes on for a long time. So it goes straight, and it gets to here, right? And then what happens? I'm going to glue by the identity map here. So it comes out here, right? And it's still going straight. So it goes straight, and then it hits, well, it doesn't hit, there's nothing there to hit, right? It's just like the equator. Nothing there to hit. It comes out here, reappears here, and returns to sender. Returns to where it left from. Just like Magellan's ship. It comes right back to where it started. And that's true for any point in the three-dimensional sphere, and it's true for any direction. Just set out, go straight, you will always come back eventually and come back to where you started. Of course, how long it takes depends on the size of the universe. And if the universe keeps expanding, you may be up against some trouble there. But if it's expanding faster than you can make progress through it, you'll never get anywhere. But in principle, you would get back to where you started if the rocket could go fast enough. Okay. So here are some advantages that the three-dimensional sphere has over normal three-dimensional. So I think we tend to think of the universe as just like three-dimensional space, the space we see around us in this room. But it probably isn't. So some advantages that the three-dimensional sphere has: it's a simple object. It's in some mathematical sense as easy as it comes. It's a compact space, and compact has a precise mathematical meaning, but in this context, it almost means what you think it means, like you could almost pick it up in your hands. It has finite volume, which seems to be an important feature of the universe. We think it has finite volume. There's no edge. There's no edges involved at all. You don't run into anything. You don't fall off, in particular. And geodesics, that is, paths that are length minimizing in the short term, are actually all closed loops, which is something that we certainly have a lot of experience of from living on the surface of the Earth. It's a little boring, but that's okay. Here's some disadvantages that it has. So the notion of curvature on a surface is easy, and I think I described it almost completely here on my shoulder. The notion of curvature of a three-dimensional object is not very different. There's three directions for things to curve in, but other than that, it's pretty much the same. And not surprisingly, a three-dimensional sphere is positively curved. Two-dimensional sphere is certainly positively curved, right? Three-dimensional sphere is positively curved also. Problem is, it seems like the universe isn't positively curved. That's kind of a catch. And we're measuring this sort of even as we speak. The WMAP satellite, that's one of the things that it's doing. It's within experimental error of being flat. So it's not a complicated question about what that means. It's essentially if you take a gigantic triangle. So if I take a gigantic triangle on the surface of the Earth, if I take a pretty big triangle on the surface of the Earth, and I look at the sum of the interior angles of this triangle, they don't add up to 180 degrees. They add up to more than 180 degrees. And that's one of the things that tells me that the surface of the Earth is positively curved. Well, if the universe were positively curved, if we took an enormous triangle, maybe like that star to that star to that star, and measured the sum of the interior angles of that enormous triangle, if it were positively curved, we would get more than 180 degrees. It's a very straightforward calculation. And the trouble is that we keep getting 180 degrees, plus or minus epsilon. So it seems like it's flat. So, but we don't really want it to be flat because we don't want to fall off the edge, and we don't want it to be Euclidean three-dimensional space because that doesn't really make much sense because Euclidean three-dimensional space goes on forever. It's an issue. So what other possibilities are there? Well, the two-dimensional torus is flat. Two-dimensional Mobius band is flat. What about a three-dimensional torus or some other possibilities? Well, it turns out there's a perfectly good three-dimensional torus. It looks, remember the two-dimensional torus looked just like a flat rectangle of paper once I finished cutting it up? Well, let's start with a three-dimensional version of that, which is just a cube, and say, okay, this is like a gigantic holographic version of Pac-Man. Except I think I'm getting too old. Has anybody played Pac-Man? Oh, that's better. Okay.
It's the slide rule people again.
So Pac-Man is really taking place on a torus, right? Here's your computer screen. Okay, this is really low tech. Here's your computer screen. And the little Pac-Man guy goes, and he disappears off here, right? And then he comes back here. Okay, now in my dream version of Pac-Man, the little Edie guy goes up here, and I know in real Pac-Man he just dies, but pretend, humor me. Where should he pop back up? Well, bottom here, right? So Pac-Man is really, if you soup it up just slightly, a game that's played on the surface of a torus. And indeed, some really sick people have made it on a Mobius band, for example. You can play Pac-Man on a Mobius band, or even on RP2, for those who are at my talk this afternoon. So imagine that we're going to make a really souped-up version of Pac-Man. It's going to take place in a room like this, except you didn't tell me it was going to be such a weird-shaped room. So I don't know. Pretend this is a normal room. And there's going to be three-dimensional little Edie guys, right? And one of them's just going to, walk out the door like this. I'm not going to do this because it takes too long. straight up here, and it'll come straight up through the floor here. There's nothing mathematically even confusing about that. It's just a model of a three-dimensional torus. And if the three-dimensional torus were large enough, it could be the universe. It has a lot of advantages. So this is well, we'll skip that one. That's the non-orientable version of the universe. Some advantages that it has is it's very simple from a mathematical point of view. Its geometry is flat, large triangles in the torus. Interior angles sum to 180 degrees. You would not be able to tell if you weren't living in Euclidean space. It's compact, it has finite volume. There's no problem with it expanding from a point at the Big Bang. That's not an issue. Disadvantages: light has to travel in a funny path. So in particular, if I shine a light that way, in fact, if I look that way for long enough, if this room is the whole universe, and I look in that direction long enough, eventually I will die, but eventually I will see the back of my head. Okay? That's what I'll see in front of me. And in fact, one of the things that has been looked at in satellites is the question of whether you're seeing images of yourself in different parts of the sky as we look far enough back. Exactly because of this question of whether light is traveling in a complete geodesic around. It's an issue to tell because you've been seeing yourself when you were much younger. Right. That would be good. Cool. Okay. So, and what happens to a rocket? Well, it also goes off in one direction, goes straight, and comes back most of the time pretty close to where it started. The twisted three torus has some distinct disadvantages, which you'll read about down there. We really hope we're not living in one of those. So, and how many? So I've just described to you one possible shape for the three-dimensional universe. How many three-dimensional manifolds are there? How long will we be here? No, I'm kidding. Well, they're an infinite number. They're all different. They're not hard to describe. We don't have a really good mathematical handle on them. We don't know which one we're living in. And the three-dimensional torus is not a bad guess at the moment. The other possibility is there's a wonderful apocryphal story, which I guess it's an urban legend about someone who, a cosmologist who was explaining the shape of the universe, probably, and a woman raised her hand and said, "But the universe is held up by a turtle." Heard this? And he said, "Yes, and what's underneath the turtle?" And she said, "It's another turtle." And the eminent cosmologist said, "And what's underneath that turtle?" She said, "Young man, it's turtles all the way down." So the other possibility is it could be turtles all the way down. So I think that's, thank you very much.